Yeah, so today I want to talk about dark energy and what we could know about the global structure of space-time. And well, I guess I'm very highly redshifted with respect to the computer. Yeah, so this is the plan. Kind of like last time, I will spend roughly half of it on setting up the sort of problem, and this will have almost nothing to do with dark energy. And then, kind of like last time, I will go through some examples where inclusion of lambda actually kind of changes things or is useful for us. So I guess it's sort of like, like in the previous talk and in this talk, we're kind of like dealing with like a non-lambda dominated era and the lambda dominated era. So I think it's the global structure of that fits some of the cosmology maybe. And in the second part of the talk, I will take you basically through 5 examples of kind of like where, like switching lambda on in some sense, and the sense will be very different in different examples. And I will show you how that kind of like changes our assessment of what can observers know about their space-time, what can be predicted or retrodicted, what can be epistemically accessed, and so on. Okay. Oh God, I think I just said a lot of this. So yeah, let me just repeat this. So I don't want to repeat this. I should not repeat this. So it's kind of like, it will be sort of like analogical discussion to what we had on determinism, but for what we can know about space-time. So yeah, I should have said that, of course, also like if lambda had the negative value, right, contrary to what we seem to observe, then there would also be a lot of interesting consequences. Our lives would be, like last time we have seen that in some ways our lives are better and in some ways they're worse because we have lambda. Because the value of lambda seems to be positive. And if it were negative, then of course it would also be, our lives would be made better or worse in very different ways, which I'm happy to talk over dinner or drinks or something. Life of string physicists would be so much better and easier, for instance, if it were negative. So poor them. Yeah, and the overall approach that I'm taking in this talk is similar. So we put ourselves into the state of mind where we see general relativity as a collection of spacetimes. And we will look at some propositions and then we'll try to see what effects lambda might have on the validity or scope or interpretation of those or similar propositions. Okay. Yeah. So now let's talk about determinism, prediction, and observation. So I think in kind of like common physics and also common philosophy talk, determinism is often equated with predictability. So a theory is deterministic. If the theory is deterministic, then we can like successfully use it to make it predictions. And sort of like vice versa, if we have a theory that's predictive, then that should imply that something like an initial value problem for that theory should be well posed, and we could use that to sort of like dynamically or in other ways generate predictions. But from the discussion that we had last time about the causal structure, I think you can like immediately point out that, well, if prediction has something to do with like solving Einstein's field equations for initial data defined on a Cauchy slice or something like that, it would be like dynamical notion of prediction, then, these two notions, determinism and prediction, they can come apart, right? Because even if the observers, even if the spacetimes that some observers, say us, live inside of, if that spacetime has a Cauchy slice, let's say sigma, we might just be unable to access all of the slice, right? So, for instance, you can imagine, like, like maybe with some degree of precision, we can access a portion of a Cauchy slice that's kind of like intersects with our Hubble bubble, but there's a lot of stuff to the outside of it, and who knows what's going to happen over there. And so this fact that we cannot, or those observers cannot access a Cauchy slice sigma might, and I think in general will, limit their predictive capabilities. even in situations where, like it may so happen that this spacetime is one of those like nice spacetimes where some form of cosmic censorship and so on holds, it's when considered as a spacetime, as a like solution to the Einstein's field equations, it's perfectly deterministic. Observers living inside of that spacetime might not be able to determine it. So in this way, the notion of determinism or the notion of prediction comes apart when we think just slightly more carefully about observers living in those spacetimes. Okay, so the second bit of kind of like general framing that I want to talk about has to do with properties of spacetimes. So, like the last time, we imagined that there is some collection or family of spacetimes, so something like, something like this is given. All sorts of things live there: cosmological spacetimes, black hole spacetimes, crazy spacetimes, and now we want to talk about spacetime properties. And so, well, property will simply be something like a sub-collection of this thing, right? So, like maybe here is the point M, well, this some particular spacetime mg, let's say it's like my favorite spacetime, whatever it is. And, we can imagine all sorts of properties defined as sub-collections of this, right? So, like maybe there's this property, let's call it Q. Maybe there's like some other property R over here. Maybe like yet another property P over here. They can intersect in all sorts of interesting ways. Then can form hierarchical relationships and so on. And maybe I should say this, that like this is a rather unstructured, very messy collection. It doesn't come with like a natural notion of distance. Some of those properties will be structured, but in general, like saying, for instance, that this spacetime is close to this spacetime may be a highly non-trivial thing. There may be no unique definition of a distance or even no good definition available for practical purposes and so on. And now, because today we're interested in, like prediction and observation and all of those things, so what we'll try to do now is we'll try to investigate some relations which link various elements of this collection. So in particular, like we'll be interested in these situations, like in the situations such as we think that we live in, let's say, in a cosmological universe, but given all of the observations that we can make or observers such as us could make, is it possible that we might have been living, let's say that the cosmological universe is this like red bubble Q here.
You turned off the...
I did?
Yeah.
No way.
Yeah, I did.
Oh no. I'm sorry.
Now it's on.
And this one is also on.
Thank you.
Yeah. So where was I? Oh, yes. So we're trying to investigate some relations linking these elements. And in particular, just to kind of like try to gently introduce you into this, we will ask whether there exists something like a relationship of observational indistinguishability. It's a technical term. Some of you are familiar with it. So I beg for your patience throughout the first part of this talk. And so it could happen that there is a spacetime, let's say, like some spacetime n h over here that stands in this relationship that it's for all, from the point of view of, let's say, maybe like every observer living in here and every observer living in here, they could just as well be living in this one or in this one. So maybe, right? It's a good question to ask. Maybe some properties of those spacetimes are underdetermined by observations. Could that happen? And of course, just to plug in the second part of this talk, could dark energy have something to do with it? Yeah, so in general, we'll be interested with something like, like different relations linking some particular spacetime with those other ones. And I will kind of like generically refer to them as forms of observational indistinguishability, but there will be different ways of kind of like cashing out that idea more formally. So there will be something like relation OI with something like some blank to be filled in front of this relation. Okay, so now I'm continuing to build your intuitions about this. So yeah, consider some spacetime mg, let's say this one, and intuitively want to say that some spacetime nh is an observation indistinguishable counterpart of mg if no observations made anywhere inside of mg can tell these two spacetimes apart. And a piece of terminology that I like a lot is due to John Norton, who calls this other element of this relation a nemesis spacetime. It's a nemesis spacetime because it's sort of like, like we imagine ourselves as living in mg, and we think, oh, here are the properties that mg has, but then a nemesis spacetime comes and like shows me that actually maybe I shouldn't be so sure about those properties holding in mg because I could just as well live in nh for all I know. And I mean, of course, all those relations will be kind of like reflexive, so that's not interesting. So we're only interested in situations where nh is different from the original one, and because we're looking at Lorentzian geometry, then something like isometry. So existence of a metric preserving function between one spacetime and another is like a good standard of what counts as the same and what counts as different. Okay. So now I guess I should say something about what are observations about. And well, at the best, observations can be about anything that could in principle be accessed by some observer. So observations should be about chronological or causal pasts of observers as imagined, or I guess to borrow Eric's phrase, schematized in some way. And, I think this is a very permissive notion of observation because our actual situation, of course, is much worse than that. We cannot kind of like freely access anything lying within our past light cone, right? We cannot go back to, I don't know, like a millisecond after the Big Bang and like find out what the metric structure was there exactly. Or like, like even when it comes to like last 20,000 years or something like this, our access to the past is highly limited. And this notion kind of like ignores that and assumes that we have full access to the chronological or causal, I guess, if you will, past. And I should also note that, just so you don't have your hopes up, this notion of observation has nothing to do like with, I mean, well, it has something to do, but it doesn't have much to do with anything like actually made observations. So like we're not thinking now about like any kind of like particular line of evidence, say WMAP or whatever, using highly precise instruments and complicated and sophisticated calibration techniques and methods of data analysis and so on. So it's a much more kind of bare bones minimal notion of what observation is about. But it's also more permissive than, than the actually made observations. Okay. Do you have any questions or comments at this point? Because now I will like throw in some formulas at you. I think we have, wow, 3 questions. Awesome.
Yes, you are speaking about a couple of space-time which are observationally indistinguishable, but not as isometric.
Yes.
So I think that it could be good to give an example, because these two properties are not completely exclusive, but it's
Yes.
very difficult to imagine a situation physically reasonable and with this kind of properties.
Okay, yes, that's an awesome point. So so what happens later in this talk is I will first throw different definitions, different formally precise definitions at you. Then I will sort of like sketch you a proof of a theorem that establishes one of them. But like, just so we have some intuition, maybe I can kind of like mine some of your, sorry?
Not as a cross line.
Not the cross line. I'll do an even simpler one, but you will see some pictures that you will recognize very well, Enzo. Okay, I will actually help myself to this relationship. So we're now considering two spacetimes. This is M, this is N. And we're only interested in the situation where for any point P in M, there is a point P prime in N, such that the chronological past of P is isometric with chronological past of P prime. And this is a sort of like really like, I'm kind of cheating with this example, but imagine this is Minkowski spacetime, right? So all of the light cones in the usual coordinate systems go at 45-degree angles, and imagine we are fixed some, let's say, some time t, and some other time t, let's say t prime in here, and we. Oh, I will just help myself to the example I used 2 days ago to sort of mine some of your intuitions. So we're now imagining like an Eric-like shape. And we can kind of compare my drawing capabilities, and they're not great. Eric was a bit conformally deformed in here. And so, so like we're taking this shape, subtracting it from the spacetime, and now we're asking, okay, is this spacetime observation indistinguishable from this one? And well, like it's Minkowski spacetime, so it kind of like, it's highly symmetric, it doesn't matter which point we take, all of the past line cones here will be basically identical unless we impose some additional structure, but let's not do that. Right? We're not thinking of this as like a background for, I don't know, stars evolving and people making choices and none of this. We're just looking at pure geometry. And so then, of course, no matter which point in here we take, we can just map this point and its causal past onto this thing in here, right? So for any point in the Minkowski spacetime, there will be a point in the kind of mutilated spacetime such that they're both chronological and causal pasts are identical, and yet this spacetime has a very different global feature because it obviously has this huge Eric shape hole in there. So these are the sorts of situations that we're imagining. So like one way of interpreting this is like, if I'm in the Minkowski spacetime and I know kind of like where exactly I am, I cannot tell if I'm in the Minkowski spacetime or Minkowski spacetime with Eric-like shape removed from it. And you can immediately notice that this is not symmetric, right? Like if I were kind of like somewhere in here and I've seen, oh no, like somewhere deep in my past, there's actually a shape missing, then I can immediately tell that I'm living in this one, not in this one. So it's an asymmetric definition. And in the rest of this talk, we'll kind of go through like more fancy pants ways of constructing these sorts of situations, including, I'm sorry to admit that, the closed line construction. This is very similar, but I just wanted to use it to kind of like bring the intuitions about. But there will be a better example of this taken from David Malaman's 1977 paper that actually utilizes something like the sitter, so that will be a bit more interesting.
But these goals in the future, in a sense, are something without physical reason, are something a bit strange. So I am not completely sure that it is possible to show equivalence as Gleiman and Malman did, basing on something that is very strange from physical point of view, not in the observable part, in the unobservable part. Okay.
Yes.
So there is, okay. This does not mean that it is impossible to find, but it is not so easy to find space-times that are observationally indistinguishable on one side and isometric on the other side.
Yes. No. Yeah. I think that's totally right. So I think this is like one of the ways in which lambda is kind of interesting, because yeah. So Enzo, of course, is like a few steps ahead of me in this talk, but yeah. So like basically, what will happen is like I will take you through the standard construction, which is the closed line construction that Enzo just referred to, and I'm not going to kind of like argue either way about its physical significance today. I think it is an interesting back and forth, but I just personally don't have an opinion on this, I guess. But kind of using lambda can, some spacetimes with lambda-like behavior might be used to make these kinds of points in a somehow more physically perspicuous way, in some sense. Yeah, I think we have 1, 2, 3 more questions.
I was not understanding why they were not so.
Okay, so well, so like just think about these two, for instance, right?
Yeah, but now I understand.
Okay,
Yeah.
right. Yeah, they're just, for instance, topologically different, right? Like this is basically up to homotopy a point, and this is a donut.
I just wanted to check if I'm getting the gist correctly, because I've seen kind of similar arguments when I read about particle identity crisis in quantum mechanics. They were arguing kind of like the same way. So if we take two indistinguishable objects, in what way we can determine their identity? Is this what it's about, or something else?
Well, let me think about this.
But this was in the context of like realism discussion. I think it's
Yeah, like indiscernible particles and this sort of stuff. I think it's quite different. I think it's more like the situation where you have like two very big objects and you only have epistemic access to portion of this object. And you want to know like, is the shape of this object kind of like uniquely determined by what I can access?
so it's all about like determining things that are very hard to determine.
Right, yeah. Or sort of like you may even think, I think it's, again, like you're getting kind of like ahead of me here, just like Enzo did. One of the kind of like interpretations of these kinds of constructions is that they establish some kind of skepticism about some properties of our universe. But you can interpret them in different ways as well. I'll get to this at the end of this section. And I think we have one more question.
My question, thank you very much for your lesson. And my question is quick and short. For all your space-times, all the dimensions coincides, all are the same, or can be x, y coincide, and we have I or K and other. You understand my question?
Yeah.
Is the same?
Yeah, so here implicitly I'm assuming that they have the same dimensionality. So I'm not thinking of like situation where like I take this, I don't know, 2 or 4 dimensional space-time, and I'm kind of like uncertain about the number of dimensions because I can embed myself into like a submanifold of another one. I'm kind of like implicitly assuming that they all have the same dimensionality, which is either 4 or 2, I guess, when I
Not
draw
only
them.
same dimensionality, but they coincide. Means that Euclidean we have 3D and time. Yeah.
I mean, it's all Lorentzian, right? So the signature of metric is
Lorentzian.
fixed.
Okay.
So
Okay.
yeah.
Yeah. Thank you.
Yeah. In that sense, yeah. All right. Any other questions at this stage? I'm happy to take questions during. Again, just reserving myself a right to say, oh, it's too hard. Let's talk about it later. Okay. Cool. So so we're here. And now let's talk about 3 standard definitions, which can be labeled like this. So the first is weak POI. So, sorry, the names, I think Eric and I kind of came up with these names. And when you first see them, they may not be like very descriptive. But basically, like weak POI is like this definition I kind of like utilize in here. And it's P from its observational indistinguishability defined along points, right? So I'm looking at a point here and I'm trying to find a corresponding point in there. And it's a weak definition because it has this asymmetric character. For every point in here, there is a corresponding point in here, but you could require that also like vice versa, that the Nemesis spacetime is observationally indistinguishable from my favorite spacetime. That would also be a sensible condition, which I hope this weak, strong terminology makes a bit more sense now. It would be stronger in the sense that the relationship would be symmetric. So it would also hold if I swapped those two in places. And and another notion that sort of like shows up in an older literature about this. Oh, and I should have said that like this way of thinking about global structure of space-time, like that really kind of like amazingly like we can like trace it to a single volume of Minnesota Studies in Philosophy of Science from 1977, with papers by Clark Grimoire, David Malamud, and Bob Garash. And it's an absolutely wonderful volume that I think everyone should read at least once. And if you have trouble finding it, Eric has a déjà vu file on his website. So the third standard definition is what we call strong COI. So now we're not looking at observers as making kind of observations along points, but we think of them as inextendable causal curves. I guess time-like in the way that Malamud put this definition. So now we're not asking about the chronological past of any point, but about chronological past of any smooth, inextendable time-like curve. And now we'll be asking whether, can I find a corresponding curve in the other spacetime? And like here, of course, like you instantly see that this is not possible, right? No matter what future inextendable curve I'm going to take, I cannot embed it in here, preserving these properties in such a way that I will kind of like be able to avoid this missing hole. Okay. Do you guys have any questions or? All right. Because if so, like I'm just happy to, yeah. All right, then please continue. Okay, so so I should make some comments about this. The first is that most of the work on the topic just assumes this weak POI notion, and by this I mostly mean like J.B. Manchak's sort of work on this that kind of like does a lot of things that I'm kind of like hand waving out here, but in a much more kind of like precise way. And of course, you could also instantly imagine something like a weak version of this COI, and as far as I know, that has just not been explored in the literature at all.
If I have a strong POI, then the NH spacetime is isometric to the MG spacetime, or not?
Not necessarily, no, and I will show you an example of that in the second part of this talk. It doesn't have to be, yeah. Because yes, that's right, like you may think, like this example kind of suggests this, right? Like, oh, maybe this is just like an artifact of this working along the points. If I worked along curves, like my situation would be better. That's not true.
Right. Is this similar, just like an injective and a bijective isometry between spaces? Is this just another way of putting this?
Well, yes, but not between the whole spacetimes, but rather between like chronological or causal pasts of certain subregions.
Okay.
Right? Yeah. Yeah. So yeah. That's one way of thinking about this. Like, can I for any point in here, can I find like a suitable immersion in something that has
For the strong COI, it's a path isometry.
I guess.
Okay.
Yeah. That's a neat way of thinking about this. Mm-hmm. All right. Oh, and I should have said, and like if you're like listening carefully to what I'm saying, you were probably already like annoyed with me. You would be like, Juliusz, why are you sometimes talking about chronological and sometimes about causal? That's so annoying. Stop doing this. And you're right. I apologize. I should not be doing this. Well, these definitions are usually stated in terms of the chronological precedence relation. So about which 2 points in the spacetime are connected by a time-like curve. But they could just as well be stated, or kind of like, I guess, something like weak JPOI, strong JPOI, and so on, stated in the terms of the causal relation, where we also allow the null curves. And I don't know, I don't think much would change. I asked this question to JB Manchak at some point, and he told me to meditate on that. So, whether that changes anything in the proof. Because it is a curious thing, because the proofs are all stated in terms of a I minus, which is a weaker relationship. So why were they not stated in terms of J? I'm still meditating on that, I guess. Yeah.
Wouldn't you possibly get different results in spacetimes that weren't causally closed?
Maybe. Maybe you meditate faster than me. I haven't spent that much time meditating on this. Also, I should meditate more. That would be good for me in many levels. Yeah. Mm-hmm. Yeah, but that's because I think it's well, these topics are fun, and like, of course, like already you see that like interesting questions kind of proliferate, right? And this is even before we went to lambda, right? Because we have question of, like which of those is good? You may ask also, are there other definitions? What happens if you switch to J? You may like Enzo be concerned, like the construction that I will kind of go through in the next 4 slides or so, like that produces a lot of these kind of space-time holes, so maybe they're unphysical, or in what sense they are holes in space-time, like what to make of them, how to interpret these results. All sorts of fascinating questions arise, and I think it will be even more fun when we add lambda. All right, so now it's time for the dreaded clothesline construction. So the idea of this construction goes back to David Malaman's paper from 1977, and it has been sort of like cleaned up and like actually carried through in a way in JB Manchak's 2009 paper, and I guess subsequent papers as well. And well, Well, the basic idea is that you take some spacetime mg, you take a bunch of copies of that spacetime, and you cut out various sort of like regions or slits in various copies of those spacetimes, and then you kind of like glue them together. So it's called a clothesline because it's sort of like as if you took like a bunch of t-shirts, put them on a clothesline, and then, you know, like you're interested in the question of, oh, like it's my favorite t-shirt, like it has some kind of like funky pattern that I really like. Like, does that pattern uniquely determine the t-shirt? And if you take enough copies of this and kind of like, you know, cut them and sew them together, you will end up with some kind of horrible monstrosity that's, I guess this is where the clothesline intuition comes from. It would definitely be unwearable, I guess. Yeah. Yeah, so how does that work? Well, you start with whatever, well, not with whatever. You start with your favorite spacetime. You just have to prove, we just have to kind of assume that you're not too extravagant, and that your favorite spacetime is not causally bizarre. So what does it mean? A spacetime is causally bizarre if there's a single point such that the whole of spacetime is contained in the chronological past of that. Sorry, causal. It's causally bizarre, so it should be causal past of that point. So it would be sort of like a situation where like there is like some kind of like a privileged event in the spacetime such that from that point of view, we can see the whole universe, everything that ever happened or will happen in it. So the construction does not work for those spacetimes, so if that's your favorite, then I have good news for you. You're in observationally a very, very good situation because no one can construct these kinds of examples against you. I guess that's the only good thing to be said about causally bizarre spacetimes. Yeah, so now assume that your favorite spacetime is not causally bizarre. And if you wish, we can kind of like try to, you know, kind of fix Minkowski or Schwarzschild or whatever, and we can kind of go through this together now. And you take some set of points which under modest topological assumptions turns out to be countable, and you cover the whole of the spacetime with chronological paths of those points, and it's a countable set, and you take 2 copies of course, those things will be like little spacetimes when considered on their own right. And so then for any of those indices, you take 2 copies, and well, then you do, I'm not sure how useful this will be for us, because actually I will not utilize this in the lambda bit at all. So then what you do is you first kind of like remove particular, in each of those spacetimes you pick some open set, remove particular subsets from it, and kind of like continue this procedure for other elements of your sequence. And then you do some identifications of top edge with bottom edges. Like it becomes a very bizarre top, bottom, like I don't know what to think about this terminology. And basically what you end up with the chain, after you do these kind of identifications, is that no matter what point and its chronological path you take, a counterpart of that sort of from the original spacetime will be found somewhere in this chain. And so that construction then establishes weak observational indistinguishability. Okay, so that is pretty abstract. So I don't know if a picture that Enza, I think, will recognize may be helpful for us. So Enza and Enrico wrote a paper kind of criticizing some of those constructions on the grounds of them having certain kinds of holes which they consider, I guess, physically inadmissible. And one of the amazing things that happened in that paper is that they actually do have like a pictorial illustration of the construction, which of course JB Manchak didn't bother to do because we should just meditate on the proof and see that. And I think it's great that they did that because I don't have to like subject you to like my further horrible drawing. So sort of like this is what happens. You have, let's say, first two copies of kind of like first element in the chain. You cut slits like this, and then you kind of like glue them, the bottom of this to the top of this, and the top of this to the bottom of this, and so on like this, and then kind of like continue for the other elements of the chain. Yeah. Okay. So yeah. So this is the construction, and again, like this is no lambda, and this is just this like one particular notion, weak POI. And now, what can be shown with this construction? So an interesting thing that J.B. Manchak showed is, first of all, for any spacetime which is not causally bizarre, in the sense that we have discussed, it's not such that all of the spacetime can be seen from a single point. It should be J there, not I. Juliusz, get your shit together. So for any spacetime which is not causally bizarre, there exists a weak POI nemesis with all of the same local properties. And if you think of intuitively, because if we look at the precise definitions, the situation becomes messy. But if you think of local spacetime properties as like roughly something that holds in the neighborhood of a point, then this construction, the closed line construction, basically guarantees that all of the local properties that hold in the spacetime will also hold in the nemesis, because we only construct the nemesis from what we had in the original, just by gluing. So that kind of is a given. And moreover, you can do that sort of exercise in sort of space-time carpentry for a cosmological model. And you could start with your favorite spacetime that's maybe isotropic and globally hyperbolic, and it's an extendable and hole-free. And then you can construct, or JB has constructed, a weak point-wise observation indistinguishable nemesis that has none of those properties. Which I guess it's an. Sorry, I should have said. I will say something about the interpretation of these kinds of stuff, these kinds of constructions on the very next slide. Okay, so this is like one use this construction can be put to. The second is you can argue that the possibility of non-trivial prediction in GR is limited to spatially compact spacetimes, which I will discuss in the second part of this talk. And you can also isolate, like Martin Lusser did, some conditions under which weak POI spacetimes actually will be isometric. So some interesting statements can be made about this. And for our purposes today, I also want to stress that all of this ignores lambda, but it will turn out that positive lambda will be useful for investigating these notions of predictions and observations kind of beyond the weak POI, and a large number of very fun examples which are not closed line-like can be constructed. I'm not saying all of them are physically significant. Some of them will be a bit trivial. Some of them will be non-trivial. But it's interesting that like a lot more can be said once we have positive lambda. Okay, and the last thing I want to talk in this part of the talk is, so what are these notions of observational distinguishability good for? Like, what's the use of that? And I have two kind of like interpretations. I should have had three interpretations, actually. So the first interpretation is a form of skepticism. So you're sort of like saying, oh, I believe in the physical significance of this construction, or like the physical but then you say that the physical significance of this construction is that, if I imagine myself as living as an observer inside my favorite space, and let's say a cosmological model, then a lot of global properties of this model are just underdetermined by any possible observations I could make whatsoever. And so, in that sense, I should be skeptical about whether these properties in fact hold in my universe outside of the tiny bit that I have epistemic access to. So I should be skeptical about whether they hold in my universe. So this is I think a fairly strong and interesting interpretation, and I think some of this will hold true in the universes with lambda. The second use would be kind of like, take a step back, not make any of those like brash, big philosophical claims, and just use this as a way of investigating dependencies between various physical concepts and notions, right? It's like, here's a physically interesting mathematical object, and we're just putting some relations on it, and it's just interesting to ask which of those can be linked by these relations, and maybe we can learn something about, I don't know, like different notions of horizons or something like that through this kind of analysis. And the third, which I haven't put on the slide, but that's sort of like what happens in part of this literature, definitely, at least in these two papers by Bob Garrosh and J.B. Manchak, is, well, like you can use these constructions to kind of poke at some of the ways of spelling out what, for instance, prediction could be in GR. And kind of there, I think the aim is, or at least one possible reading of some of those papers is that the aim is not so much a skepticism, but rather, oh, here we have like a plausibly looking definition of what prediction is in GR, but it runs into these problems that we can partly construct with this, with the helps of this method. So was that definition so good in the first place? Then it's kind of like more like analytic philosophy kind of counterexample based intuition mining, I guess. Okay. All right. Yeah, so we went through these characterizations of observations which are very minimal in one sense and very permissive in another. And we went through kind of like a bunch of different notions and through a particular construction. And now we want to, and the construction, it's a fun construction, but now could that only, like that construction worked for a particular notion of observational indistinguishability, for this like weak POI notion. Now, could something more be said about those other notions, or maybe, maybe those like 4 definitions, or I guess 8 if you go for definition with J rather than I, like, is this all that could be said about observations? Are there some alternative notions? And like, what happens, if we now think about these results, just for a moment, and because of course there is some literature that some of which was already invoked earlier on, and some which I haven't invoked, and like some back and forth about what's a physically reasonable or physically sensible spacetime, which I think is a very important and deep and hard question. And one way of approaching is through like these sorts of examples. But if we just for a moment think about this as showing some kind of, in principle, limitations to what observers could know about their spacetime, what if there was lambda? What if there was positive cosmological constant, either everywhere in the spacetime or in some subregions of the spacetime? And like this will, I think, become that bit which is very cryptic in some regions will become apparent in my example 3. So, okay, yeah. So what changes when we have the positive cosmological constant lambda? And I want to take you through 5 examples. So and after this I'm done. The first example. So I took you through all of these like formulas and the construction, and I just realized that a flaw in this presentation is that the first of those doesn't utilize these notions at all. But I think it's interesting nevertheless, and it has something to do with what we have discussed 2 days ago. So now let's think about retrodiction, so kind of like investigation of what happened in the past. So consider an observer living in some spatial volume, like V late time, in a late stage of an expanding universe, And sorry, this is not on the slides, but this is the sort of situation where we imagine ourselves as inhabiting one of those universes in which those cosmic know-how conjectures I have discussed last time are true, right? So if you don't remember what those were, these are those situations where the future behavior becomes dominated by the cosmological constant, and like no matter how kind of like funky and squiggly and complicated the initial, some kind of like finite initial volume of, I guess, of space, let's think of them as just like spatial slices was, for very late times, we can be sure that it asymptotically converges to the de Sitter solution, because what lambda does is that it makes all of those anisotropies and inhomogeneities kind of like wash away, because it's a true constant and it just dominates the future behavior of the matter. And we're talking about, you know, those conjectures and how they're true, and it's, I think it will be a bit important here to recall that the convergence was not a global convergence, it was a statement about finite volumes and their future behavior. And we're thinking, maybe, I think I haven't used this terminology, but we can think of this like lambda-dominated universe as kind of like an attractor for the solution. So now, what happens if you're an observer living in some of those like very late time volumes? In particular, what if you had like full access to what happens on that late slice, but maybe you were not concerned with anything that happened in your causal past. And imagine also that you had only you could only make measurements with finite precision. Could you kind of like uniquely retrodict your past? In other words, on the basis of the information confined to that late slice, could you make statements about what your causal past is like? And I think it's interesting to point out that you couldn't do that. There's a curious asymmetry between the causal past of this volume, J minus of VLT, and between what you could, as such an observer, plausibly determine about your causal past on the basis of finite precision of measurements confined to VLT. Because that particular late state will be compatible with very, very different initial conditions on like whatever it is that your volume was in earlier stages of the universe. And in particular also with very different evolutionary histories of it. So to speak, traces of the past of V have been washed away by lambda and can no longer be accessed only on the basis of information that's available to you at this late slice. So here's a sort of like a pictorial depiction of what happens, right? We have this spacetime M1, G1 and this other spacetime M2, G2. And we're thinking of those as kind of like one of the set of solutions that exhibit this cosmic know-how theorem-like behavior, cosmic know-how conjecture-like behavior to the future. And you know, like they could evolve, of course, from very different initial conditions. Some are rather simple, some are rather complicated. But because the late time behavior, so this box VLT in the first spacetime and in the second spacetime will be up to, for sufficiently late stages of the exponential expansion, identical to any finite precision of measurement whatsoever that you may like. And although, like, of course, this one evolved, you know, like from this initial data set through a particular trajectory, and this one evolved from a very different initial set through different particular trajectory, in particular, and of course, the causal paths can be very different. The state that you have access to at the late time will be, for any measurement made with finite precision sufficiently late, indistinguishable. And so, in the sense, let me just make this like final statement. In the sense, I think what is going on in these models is that lambda makes it impossible to retrodict your past based on information entirely contained on this on this finite volume for sufficiently late time slice. All right, Enzo.
Yes, since he's and it is obviously realistic, finite capacity of precision of measurement, the fact of their incapacity of retrodict is already warranted. But indeed, with the strong dilatation of the universe, this problem of retrodiction became very, very strong. So
yes,
this is the point, okay?
Yeah.
Because you say
Yeah.
you say about in the bias of Fahrenheit that is compared with very different, because different is enough the lackness of precision. Very different because there is also dilatation, okay?
Right.
Okay, thank you.
Yeah. So like, when I mean very different, it's like, like, oh, maybe we were in a very complicated state, like here and now, and we end up in this asymptotically de Sitter for like, I don't know, like Milky Way, let's say. Milky Way galaxy ends up asymptotically de Sitter kind of like state sufficiently far. And now we imagine ourselves as somehow surviving to that very late epoch. And we're like, oh, okay, like where did we come from? Did we come from Milky Way, or did we come from some kind of like very homogeneous state? And if we only have access to the information at that later point when we ask the question, we can just never determine the answer to this. And so before I get to Eric's question, I think this failure of retrodiction is in a way kind of like an inverse to what some philosophers think is a plausible view about future. It's sort of like the inverse of the open future view, so to speak. It's like almost like the past is kind of like inaccessible to us, and from the point of view of that late time, could just as well be this trajectory or that trajectory. In a way, past becomes underdetermined as well, which I think is philosophically funky. I think philosophers, not everyone, Łukasiewicz was open to this sort of past, and actually also people like Borges in his story, Garden of Forking Paths, allow this sort of like branching of possibilities, both to the future and to the past. And somehow, most of philosophers who think about these questions prefer to have this strong time asymmetry. And I think this is one way in which this like asymmetry between past and future is broken in an interesting way. Eric.
So there's a similar failure of retrodiction for systems that where the second law of thermodynamics is applicable. So if if there's a glass of water on the table and it's in equilibrium with the room, I have no idea whether it used to be hot and cooled down or used to be cool and heated up.
Right.
I'm curious. Do you think that given all the kinds of speculation people are engaged in these days about analogies or connections between gravitation and thermodynamics, that this might plausibly be, this kind of failure of retrodiction might plausibly be interpreted as having a thermodynamical character?
That's a great question. Yeah, I guess so. I think it's like one way of looking at this. So like in the context of cosmic no-hair theorem, there is like a derivation of the theorem that also assumes a forms of generalized second law, which I'm not like very excited about that particular derivation. In particular, it's like never very clear to me like why the Sitter state would be the maximal entropy state, and also like why it would be like a particular numerical value of lambda. Like why shouldn't we not only converge to lambda, but lambda should also become bigger if it's like truly like entropic like behavior. Like that's never been like very clear to me. But I guess I could think of this as some form of gravitational entropy, like being like an attractor of the solution, and then it becomes quite analogous. And it would be easier for me to think about this in the like standard black hole no-hair situation. So that's a situation, right? Like when we have a collapsing star and most of the information about like particle numbers and all of the like books and trash I threw into the star, that gets kind of like washed away, I guess. Well, what happens to it in the collapse is a sort of tricky question that takes us to like black hole thermodynamics and so on. But from classical GR point of view, the end state is just like three parameters, mass, charge, and angular momentum. and like all of those other information is sort of washed away. And so I guess like one way of looking at this would be sort of similar failure of retrodiction, unless I have like access to some of the traces of the collapse process, then I would not be able to tell where the black hole came from if I just look at that single isolated black hole. Although, sorry, I'm starting to ramble, because some of those situations could be sort of like we could kind of like constrain the supermassive black hole formation channels. Depending, like if they grew by accretion, then they should have different parameters of spin than if they grew primarily by merger. So some sort of statistical information could be decoded, but yeah, the access to individual parts of the system, I guess, is lost. Although in the GR case, like it's sort of like it is preserved on the Cauchy surface, it just becomes like it goes arbitrarily far away from the system I'm considering, I guess, which would be like an analog of this like finite volume box, I guess. Yeah. Yeah. Yeah, maybe someone should write a paper to like annoy philosophers who think that the past is just out there and fixed, then could be fun. Yeah. I don't know if this answers your question, really. Does it answer your question? Yes. Cool. All right. So, yeah, so I think this is like one way in which, you know, like once we switch the lambda on, the answer becomes like the answer to what we could predict, or in this case, retrodict, becomes slightly different in an interesting way. Okay. So that was retrodiction, and now we want to talk about possibility of prediction. So there's a kind of characterization of prediction. Well, it's not really a single notion, it's kind of like a family of notions, but the basic gist of this is that like from this sort of like, if you think about what does it mean to predict something in general relativity with this kind of like global structure of space-time background, then you may be tempted to think about prediction in the following way. So you define something like a domain of prediction for some point P, and you think of the domain of prediction, maybe I should be like kind of like drawing it. So here's some point P, sorry, some point Q, and we want to know what the domain of prediction of Q is, and you think of this as like some subregion of this space-time. So the set of points P which are, well, where should they be if we want to make predictions? They should not be in my causal past, right? So they should be not in here. And I guess partly because I can think of this as in the following way. I think of my causal past as a region on which I have collected the data, and now I am here and now at this point Q, and I want to make prediction about something that happens in the future. And moreover, for the prediction to be kind of like, I guess, like 100% reliable, like predictive in the like physics sense, it's something that I can like precisely calculate and determine. The prediction should be made on the basis of some sort of a surface, which may be a, well, I guess it should be at least a partial Cauchy surface, so it should have like non-empty domain of dependence, which I hope you remember from 2 days ago. So the domain of dependence is the set of points such that no matter, no matter how you draw inextendable curves through it, they will have to be kind of like captured and intersected exactly one with this surface. And so there is a surface sigma somewhere. Let's make it this purple surface sigma here, which satisfies some technical conditions which will not be super important for us, and such that the point about which I'm making a prediction, like, you know, whether I will be able to make it, I don't know, like on time to the airport tomorrow or whatever, like this point should be somewhere in here, and that point should also be in the future domain of dependence of the surface sigma. Because under those conditions, it's kind of like, and of course the surface on the basis of which I'm making a prediction should be also in my causal past. Right? So I collect all sorts of information. I'm here and now at Q, and I can make statements about what I can predict on the basis of the surface sigma within its domain of dependence. Because if, I wanted to borrow Slava Mukhanov's terminology, and I think, okay, yes, that happens on this slide. And so I'll get to the garbage point in just a moment. So under some minor further technicalities, because you can add like various adjectives to these definitions, which is formally important, but for us, for the point I want to make about lambda on the next slide, not very interesting. But under some minor further technicalities, it turns out that the domain of prediction seen in this way is very small. It's basically the boundary of this domain of dependence. Unless there is kind of like a more fortunate situation, namely there is a compact Cauchy hypersurface for this space-time, which is confined to the causal past of the point at which I'm making the prediction. And I think you can think of this, in a kind of like Slava Mukhanov sort of way, because you can kind of like, like if this thing is not a Cauchy surface, then there may be, like all sorts of, do I have another color? I don't have another color. Let's work with this one. Like there may be all sorts of like space-time garbage, kind of like, flowing in from there, from outside of this region that I have access to outside of the surface. And that can I don't know, screw me up in all sorts of ways. I don't know, maybe I'll get hit by a very fast traveling meteorite that I didn't bother to, that kind of flies outside of my causal past and hits me on the way to airport tomorrow or whatever, right? All kinds of space garbage can come in and screw my prediction. And this is kind of like an intuitive characterization of what happens, but one of the kind of more formally perspicuous way of proving that would be with the closed line construction, unfortunately, or other kind of manipulations like this. So the domain of prediction is very small. It's basically confined to the boundary of a domain of dependence. Because I can never rule out some cosmic garbage coming from the outside. I mean, I guess I could, wave my hands about, maybe it's an atypical situation and I should just assume that everything kind of disappears farther away. I don't know, maybe it becomes asymptotically flat because I'm isolated from the rest of the universe on my way to the airport tomorrow or whatever. It sounds a bit silly, but that would be invoking a ceteris paribus clause and kind of try to get around these objections in that way. I don't think it's a very successful strategy, but you could. I guess there's a lot of other things to be said about it. But modulo these sorts of moves, I can never be certain about there being some kind of garbage coming from the outside and screwing with my predictions. Unless I'm in the kind of fortunate situation, which would be like this. Maybe the space-time I'm living in is actually spatially compact, right? I don't know, here's the Big Bang or something like this. Here's my past light cone kind of early on at point Q1. And, well, insofar as I'm there, my capability to predict things is very small, right? This is my surface, and so the domain of dependence of this is plus its boundary is the only thing I can control. But then, maybe as I'm getting older, I learn more about the universe, like this. And at some point, I realized, oh, actually the universe is spatially compact. It's spatially closed. And it actually does have some kind of like a surface here, some kind of surface sigma. And so it's sort of like, oh, I wasn't aware that it's spatially closed at this early time, but here at this later time, I realize it's spatially closed. And in this way, I don't have to worry about cosmic garbage anymore, right? Because everything that's out there in the universe is sort of like accounted for on this later surface sigma. And then like my life becomes wonderful again because I'm kind of like, then the domain, if I have full access to the Cauchy surface, then the domain of, if it's a Cauchy surface in the space-time, then I have access to everything that happens. So that's great, right? I mean, at least that's a better situation than I was in before here, and it's a much better situation than the cosmic garbage kind of situation. I should do like a bit of due diligence to people like Bob Gorosh and J.B. Manchak because they thought of this, well, okay, maybe it is a Cauchy surface, but can I know that it is a Cauchy surface? And then my situation is bad again and messy. But the upshot for us in the context of this example too is that having a compact Cauchy surface which I can observe from a single point would improve my epistemic situation because the possibility to predict in a sense close to something like this notion of prediction just becomes much better. Okay, so compactness seems necessary for, I should have said something like a non-trivial prediction, so like going outside of this boundary here in this sense. But is compactness sufficient? Not necessarily. So what I will now argue is that we can, if the lambda is positive, and even if we're living in a universe with like a compact space-like section, even if it's a global hyperbolic and as nice as we want, everything is well posed, our epistemic situation can still be pretty bad, at least with regard to some global space-time properties of that universe. And so how to see that? Well, the first step is really non-trivial because it invokes a highly complicated theorem by Hans Ringstrom, and Eric already invoked that theorem and showed a more precise version of the statement. But basically the theorem states that for a particular type of a matter system, you can take you can construct a family of cosmological models, all of which share a number of features. They're initially expanding, globally hyperbolic, future complete, and in that situation, a large variety of spatial topologies for the compact space-like section is compatible with observations made at any finite distance from the initial singularity. And so this is a sort of like a situation where it's kind of like this, but the expansion of the universe sort of like makes it impossible for me to actually access the space-like section and investigate all of its properties, in particular the shape of this thing. Okay, so what do we learn from this? I think the first thing we learn from this is that for some space-time properties, such as the shape of the space-like section, we could establish a form of observational indistinguishability, or a form of underdetermination can be established using different methods than the kind of clothesline cut and paste kind of construction. In this situation, this form of underdetermination of spatial topology seems to arise dynamically. So by this I mean we're not, cutting and pasting and gluing some Lorentzian manifolds, but we, or rather Hans Ringstrom, actually goes through the effort of posing a dynamical problem for the Einstein's field equations and solving it and investigate the resulting family of solutions. So from this point of view, some form of observational indistinguishability can also arise not only from this sort of like global space-time structure view that I assumed in this talk, but also from a kind of like more dynamical perspective from the point of view of like solving the initial value problem in GR, which is sometimes called the PDE view, and Klaas Landsman in a recent paper very nicely reports on some of the features of that view. And another thing that I think we learn about what we could know about our universe is that some important global properties can be shared between distinct observation in distinguishable spacetimes. All of those models are global hyperbolic, future complete, and so on, and yet they differ in some other interesting features, such as the topology of the section. And from the point of view of prediction, I think we learned that positive lambda can just make it impossible to access spatially compact hypersurfaces and can kind of screw our possibilities to predict in that way. All right, that was example 2. Now, example 3. So in example 3, we're like back to this 3 different definitions of observational indistinguishability. So now we're no longer looking at points, we're looking at future inextendable time-like curves. And now we can ask, okay, like, and I think I was already asked this, and like, can we actually find non-isometric, so globally very different spacetimes that will nevertheless be strongly observation indistinguishable as considered along curves? And now the answer is positive. So here's kind of, this construction is taken from David Malament's paper, and what he does is he considers he starts with first building blocks for the spacetimes, and there will be slabs A and B. So slabs A will be basically the de Sitter metric, and slabs B will be quite similar metric, but with all sorts of wiggle factors, and they will have the property that the metric on slab B approaches the metric of A along the borders, and so we can glue these slabs together. And but this metric B has kind of an extra wiggle factor, and so that changes the shape of the light cones in there, and of course, this wiggle factor is arbitrary. And then what happens is, here's maybe a slightly better illustration of this, is that we're now taking various infinite sequences of those slabs and glue them together. And as long as there will be at least one token of each slab, any infinite sequence whatsoever will be there. So, it would be like A, B, A, that would be one sequence, and the other would be B, 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 A. And another possible sequence would be AB, 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 AB. And I will stop making those noises because they sound kind of funny. But, we can just take these slabs and glue them together. And it turns out that chronological past of any observer will be either A slab, B slab, or that should be BA, not BS. I do apologize, David. So in the sense, if this is my original spacetime, it will have strong COI nemesis in there. And we have this strong COI nemesis because basically we started with de Sitter or de Sitter-like spacetime, so they will have cosmological horizons past which the observers in there cannot see. And by gluing the slabs in this way, they can be very different sort of metrically. It's a very different thing to have something like 2 slabs B glued together versus 2 slabs A, then B, then A. Those are just very different patterns. Okay, so I think it is pretty cool because, because what do we learn from this? Well, we do learn that we can like produce examples of observational indistinguishability not only along points but also along curves, and it seems that lambda plays quite significant role because we have been utilizing, or David was utilizing, de Sitter spacetimes in this, and the cosmological horizon of de Sitters seems basically indispensable for this construction. And we also have an example of a strong COI Nemesis spacetime. So that's pretty cool. And we have like an explicit example utilizing lambda that shows us an instance of this like strong COI under determination. Okay, I'm almost done. I have like 2 further examples I want to take you through. So this will be a slightly funky one. So now we're imagining a black hole spacetime with just standard asymptotically flat exteriors. It's like an isolated system. Everything becomes flat and Minkowski far away from there. And we consider, let's say, a single observer traveling along a curve with finite total acceleration in that spacetime. And we assume that they remain in the exterior. And if this is like a Schwarzschild spacetime, which is like this, then like any such observer will kind of like travel somewhere here to the time infinity, and we assume that they remain outside of the event horizon. Now, from the point of view of that observer, what happens in black hole interior? In particular, could they make any statements about the black hole singularity occurring inside of it? Well, of course, what they could do is like what we do, and we could just kind of like say, oh, I believe in classical general relativity and in the singularity theorems, and kind of like extrapolate that over there to the interior, and on that basis, kind of like form my belief that these forms of black holes exhibit space-time singularities on the inside. But, and I think this is like a very commonsensical conclusion, the occurrence of a black hole singularity is undetermined, in a sense, fairly close to COI. So here's what a funny model that can be explicitly constructed. So what you do is you construct what is known as a regular black hole, and the difference between the regular black hole and this black hole is just that. So like somewhere in order to get the formation of the singularity, we sort of like heuristically believe that in particular the null energy condition has to be satisfied, and you're familiar with energy conditions from Eric's talk on the first day of the summer school. But so now what you do is you say, oh, but maybe the energy condition is violated. Maybe it's violated in an arbitrarily sort of like strong way, and if that is the case, then the singularity could be avoided. And well, there are like different ways of constructing these models of black holes with regular space-time interiors. But 2 important features will be kind of like useful for us here. The first is that the energy, this region that violates energy conditions can be pushed up as far into the interior as we want. And so what this immediately implies that for an observer who stays in the exterior, they cannot see that difference. And although like in this particular citation, the asymptotics in the interior is Minkowski, in most of those models, the asymptotics is actually de Sitter. And this is because those models are sort of like intended as kind of like something like effective quantum gravity models. What would the space-time look like effectively if some speculative repulsive quantum effects were true? And it's just the easiest to kind of like do that with the de Sitter asymptotics, because what is repulsive if not positive lambda, right? Yeah. Okay. So what do we learn from this kind of an example? Well, first of all, it's strongly COI in the sense that I have discussed for any observer confined to the exterior of a black hole, right? Because the sort of like the only difference between these two diagrams is deep here in the interior, the red part here versus black part there. And if that can be pushed arbitrarily far deep inside, then for an observer traveling along this curve, gamma, they have just no way of seeing this whatsoever. I'll ignore the second point because I don't have time for this. But I want to stress that this form of observational indistinguishability, I think this should not bother us. It's, it's kind of like very different from this form of interpretation of those Klopfstein constructions established in skepticism about global spacetime properties. I think it's something that we should exactly expect. Like as long as I'm in the exterior of black hole, as long as those physical effects do not propagate outside of the horizon, I should just, like, that's the fact that I cannot exactly tell what happens in the interior without jumping in there and checking myself is exactly what I should expect. So this form of observational indistinguishability, I think it's just commonsensical. And I should just note that there are at least 4 other examples of Nemesov black hole spacetimes, but they don't utilize lambda, so I don't want to talk about them today. And the very last one I want to talk about is this thing. So let me erase this again. Okay, so now we have seen some of those like plausible definitions of observations and have seen some of those features, some examples, some explicitly constructed ones, some properties are related, some properties are shared. It's a lot of fun, but I think a natural question to ask is, well, are there other similar notions? Like, is this sort of like logical space of kind of like ways of thinking about observation and prediction kind of like exhausted by these like strong and weak POI and COI kind of notions, or is there something else? And well, there is at least one. So you could imagine something like the following. Here's some spacetime mg. Let's think of this again as the flat Minkowski spacetime, and we consider some point P in here, and we what we do is we construct the set H, which will be defined in the following way. We take every time-like geodesic from P, so sort of like staying within its future light cone, and so we take the set of all of those geodesics and we follow them to the future for some maybe small, maybe large, but finite amount of proper time. And so in the Minkowski spacetime, it looks like, like you could go up to here by some time t, or maybe up to here, or maybe up to here. And the shape of this thing will be these sorts of like hyperboloid that that sort of like asymptotically approaches this null cone. So which is why with Eric we call this future t or future tau hyperboloid. So that's the FTH. Because in Minkowski spacetime it sort of looks like this. And so now the interesting feature of this thing is that in some situations, actually, if this thing has a Cauchy surface, like this, then the causal path of this set H can actually contain the Cauchy surface. And so in this way, we can kind of like demand that the sort of like possible nemesis spacetimes are invariant under this sort of object, that they share the same future tau hyperboloid, and I'm ignoring all of the other ones. And that kind of makes my situation better in the sense of ruling out some of the examples. And this set H can be interpreted in sort of like two ways. The first is model. I'm here and alone in the space-time, but I'm kind of like undecided, should I go here or should I, you know, like run a bit faster to the left or to the right or really fast to the right? And then I'm kind of like making my observations about space-time from whatever I would have gotten in that case. And the sort of second interpretation is like, you know, like here we are, all of us, and we're concerned about observation and prediction. So we like very quickly, or some of us very quickly, some of us very slowly, run away in different directions and then start making our observations and kind of like try to constrain the space-time in this way. So this is an interesting object because in a way it improves prediction. Under these notions of predictions that we have discussed under, I think, example 2, like prediction was sort of like tied to the occurrence of a compact Cauchy's hypersurface. But under this, if something like this makes sense as an object to work with when thinking about prediction, a non-compact Cauchy hypersurface can be contained and actually is in, for instance, the Minkowski spacetime or similar spacetimes in the past of this object. Okay, so that sounds like a great news, but unfortunately, that cannot help us much if the cosmological constant is positive. Because in that situation, right, like if I'm an observer here and the universe is dominated by lambda, then this means that there will be a cosmological horizon, and no matter how far I run in any direction whatsoever, I just cannot outrun it. And so even if there is a Cauchy surface in my spacetime, I just cannot see it using this technique. And so in this way, the positive cosmological constant screws up my ability to make predictions again. Okay, yeah, so I'm almost at the end of it. I think what happens is that, you know, in the context of questions concerning prediction and observation of various global spacetime features, what we have learned is that, first of all, positive lambda shows up in many constructions and arguments, like the Malament construction, like Ringström's results, and so on. And I think here the typical result is that our epistemic situation is made worse because of the presence of positive cosmological constant. And I think it's philosophically and physically remarkable that something like this happens. And I just want to, because it's a summer school and, you know, some of you may be annoyed with this, some of you may be interested in this. So I just want to plug in some kind of like further resources for like this way of thinking about interpretation of GR. The first is J.B. Manchak's book. It's a short book. It's in this like great series of that CUP puts out, Elements in Philosophy of Physics, I think, or something like that. And I think it's a really wonderful kind of like introduction to a lot of the notions that I kind of like hand-waved about. And the second book is a recent book by Gordon Bellot about accelerating expansion, philosophy and physics with positive cosmological constant, which I think is a really great book as well. And it takes you through a lot of interesting features of the Sitter solution, various coordinate representations, the Boltzmann's brane problem that we didn't talk about, some of the stuff I have been talking about, and a lot of more. I think it's a really wonderful thing. And the very last thing is, because it's a summer school in philosophy of physics, but you know, some of you may not know about this. There's like, in these days in philosophy of physics, kind of like post-pandemic, there is a lot of online events, seminar series, reading groups, and so on. And so I kind of like keep a list of some of them on my website. So for those of you who might be interested in studying some of this further, that may be a useful resource. And yeah, I think that's it. I just have some references, and I'll shut up now.